In this lesson, we'll explore exponential and semi-log graphs, what they are, how they work, and why they matter. This video will help you approach these graphs with less stress and more confidence. You'll practice applying the concepts through targeted problems designed to build your intuition. Then we'll tackle an MCAT style passage together and break down each question step by step for deeper understanding. Let's dive in. On this slide, we're going to define exponential decay graphs. When you hear the word exponential, what comes to your mind? Exponential or exponent are closely related. Exponential means that the quantity of something changes according to an exponent. Specifically, it involves an expression of the form e raised to a variable, in this case, time. This is why it is called an exponential function. The graph of an exponential function typically takes on a backward J-shaped curve. The word decay in exponential decay tells us that something is decreasing or breaking down. This refers to the fact that the graph slopes downward. It has an overall negative trend. The formula used to represent exponential decay graph is AF is equal to AI times e to the power of negative k times t. AI is the initial amount of the substance, AF is the final amount of the substance, k is the decay constant, which usually has a positive value, t is the time elapsed, e to the power of negative k times t is the exponential decay factor. The negative sign in the exponent minus kt tells us that the quantity is decreasing, which matches the downward shape of the graph. Now let's explain the graph shown here. The y-axis represents the final amount of the substance, and the x-axis represents the time elapsed. The graph takes on a curved shape. It decreases sharply at first, then the rate of decrease slows, but it never quite reaches zero. Exponential decay means that the starting amount decreases by a fixed proportion over time. Notice that we use the word proportion and not amount. Let's look at an example to make this clear. Suppose we start with an initial amount of a radioactive substance such as uranium. Over time, the substance undergoes radioactive decay and it transforms into another substance. The amount lost does not decrease by a fixed number each interval, instead, it decreases by a fixed percentage. For example, if the substance has a half-life of about 10 minutes, then every 10 minutes, the original amount is reduced by 50%, which is a fixed proportion. The substance begins at a high concentration, and as time passes, its amount decreases. But not by a constant amount. It decreases by a constant percentage. This is why the graph has a steep slope at the beginning, indicating rapid early decay, followed by a gradual flattening slope, which reflects slower decay over time, as shown by the yellow tangent lines. So, to summarize, an exponential decay curve decreases by a fixed proportion or percentage over time. It does not decrease by a fixed amount. It has a constant half-life and a characteristic curved shape with a rapid initial drop followed by a slower decline. So you might be wondering, why do we even need to learn exponential decay graphs? On the MCAT, these graphs actually show up in several important places. Here are some of the most common places. One, inside the text passage, they may show you data in exponential form. Two, radioactive decay questions. Three, drug elimination and first order pharmacokinetics. Four, bacterial die-offs or population decline. Five, capacitor discharge in basic physics. And six, any first order decay process. All right, now let's move on to semi-log plots. On this slide, we're going to learn about semi-log plots or graphs. The word semi means half, partial, or partly. In a semi-log graph, only one axis is on a logarithmic scale, usually the y-axis, while the x-axis stays normal and linear. Semi-log graphs come from taking the natural log ln of both sides of the exponential decay equation. The exponential decay equation is AF is equal to AI times e to the power of negative KT. So let's break this down step by step. In step number 1, we need to take ln of both sides. When we do that, we get a formula listed as ln of the A final or AF is equal to ln of the A initial times e to the power of negative k times t. In step number 2, we need to apply log rules to get ln of AF is equal to ln of AI minus k times t. In step number 3, we need to rearrange the formula to get ln of AF is equal to minus k times t plus plus the ln of the initial amount, which is AI. This is now in the form of y is equal to mx plus b, which means that the exponential curve has become a straight line when graphed on a semi-log plot. And just to note, you do not need to derive the linear line formula or the equation on the MCAT. I'm just showing the steps here so you can see why exponential decay becomes a straight line on a semi-log graph. So here's the graph of a semi-log plot. On the graph shown here, the y-axis shows ln of AF and the x-axis shows time. The graph follows the straight line equation of y is equal to mx plus b. This is the reason why it appears to be linear. The negative slope tells us it's still a decay process, just like the exponential curve. The semi-log plot decreases by a fixed amount per time interval, which produces a linear graph of the exponential decay data. Semi-log graphs are helpful for finding the decay constant k, estimating half-life, and making exponential decay look linear and easier to analyze. Now that you know more about exponential decay and semi-log plots, let's work on some practice problems. And as always, take some time to answer the questions on your own before you see the solution to these problems. So here's question number 1. It reads, if the decay constant k increases, what happens to the exponential decay curve? A says it becomes steeper and decays faster. Answer choice B says the curve becomes flatter and decays slower. C says the curve becomes linear on a normal graph. And D says it no longer follows exponential behavior. Which one do you think is the right answer choice? Pick one and let's review the solution together. So you can answer this question using two methods, a conceptual approach or a mathematical approach. Let's use both to arrive at the correct answer. So conceptually, if the decay constant K increases, the substance decays faster. A faster decay means the graph drops more quickly, producing a steeper slope. This matches answer choice A. Now let's confirm this mathematically using the exponential decay formula that we presented before. The AF is equal to AI times e to the power of negative k times t. We'll plug in two different values for the decay constant. One small, k is equal to 0.1, and another one large, k is equal to 1. And then we'll compare the final amounts after the passage of the same amount of time. Let's assume the initial amount is 100 grams and the time is 1 unit of time, or let's just say 1 hour. In case number 1, for smaller decay constant of k is equal to 0.1, we plug the values into the formula to get AF is equal to 100 times e to the power of negative 0.1 times 1. And that 1 is equal to the unit time, or 1 hour. This gives a final amount of approximately 90 grams. So after 1 unit of time, or after the passage of that 1 hour, the substance decreases from 100 grams to about 90 grams. And in case number 2, the larger decay constant of K is equal to 1. When we input all the values into the formula, we get AF is equal to 100 times e to the power of negative 1 times 1. This gives a final amount of 37 grams. So with a large decay constant of 1, the substance decreases from 100 grams to 37 grams in the same amount of time. As you can see when comparing these two cases, a substance with a larger decay constant has a smaller final amount after the passage of a certain amount of time compared to the substance with the smaller decay constant. So this means that a larger decay constant produces a faster decay and a steeper slope. Although all exponential decay graphs start with an initial steep slope and eventually flatten, we're comparing the initial rate of the decay between two substances. The one with the larger K always drops faster and therefore has a steeper slope. This is why the correct answer to question number 1 is A. Here's question number 2. It reads a drug follows first order elimination. If its initial concentration is doubled, what happens to the half-life? Does it double? Does it get halved? Or does it stay the same? Or does it become zero? So to answer this question, we need to recall a key relationship from the first order kinetics. For a first order process, the decay constant K and the half-life T1 half are related by the following formula. The K is equal to ln2 divided by T1 half. If we rearrange this, we get T1 half for the half-life is equal to ln2 divided by K. This equation tells us something very important. For first order process, the half-life depends only on the decay constant. It does not depend on the initial amount or the concentration of the substance. Now the question asks what happens to the half-life if we double the starting concentration. Since half-life for first order kinetics is completely independent of the concentration, doubling the initial amount has no effect on the half-life. So the correct answer is C. It stays the same. Here's question number 3. It says, what does the slope of an exponential decay curve represent for a substance undergoing radioactive decay? Answer choice A says the slope of an exponential decay curve cannot be determined. Answer choice B says the slope is equal to the decay constant. Answer choice C says the slope represents the rate of change in the amount of the substance over time. Answer choice D says nothing meaningful can be determined from the slope because it is not constant. An exponential decay graph is not a straight line. It's curved, which means that the slope is not constant. The graph starts with its steep slopes, showing rapid early decay, and then gradually levels out into a flatter slope as the decay slows down. This changing slope represents the rate of change of the substance over time, and this is exactly what answer choice C says. Answer choices A and D are not correct. They are wrong because the slope of an exponential decay graph does tell us something meaningful. Answer choice B is also not correct because the decay constant is not the slope of an exponential curve. So the correct answer is C. Here's question number 4. It reads, scientists studying the growth of Pseudomonas aeruginosa tested the effectiveness of two antibiotics, penicillin and ciprofloxacin, on reducing the size of bacterial colony. They found that the ciprofloxacin decreases the time required for the colony to shrink to half its original size by a factor of 2 compared to penicillin-treated group. Based on these results, what can be concluded about the semi-log plot of bacteria treated with ciprofloxacin compared to penicillin? Answer choice A says the graph will start at a higher value for the ln amount of bacteria for the ciprofloxacin group. Answer choice B says the slope of the semi-log plot for ciprofloxacin will be more negative. Answer choice C says the slope of the semi-log plot for ciprofloxacin will be less negative. And answer choice D says the graph for both antibiotics will have the same slope but differ only in curvature. Which one do you think is the correct answer? Come up with your reasoning and then let's go over the solutions together. So, what is this question really asking, and how can we arrive at the correct answer? This question wants you to determine how the semi-log plot of bacteria treated with ciprofloxacin will differ from the plot of the bacteria treated with penicillin. To answer that, we need to focus on two key factors. One, the experimental result, and two, what the question is asking us to compare. The question states that ciprofloxacin cuts the time required for the colony to shrink to half its original size by a factor of 2 compared to the penicillin treated group. So, what does that actually mean? Anytime a question talks about how long it takes for something to reduce, decrease, die off, or shrink to half its amount, it's referring to the same underlying idea, the half-life of the process. So even though we aren't using the term in the question stem, but this is referring to half-life. Now, how does this relate to the semi-log plot? On a semi-log plot of the ln final amount versus time, the straight line slope is determined by the decay constant k from using the equation of the ln AF is equal to minus k times t plus ln of AI. So this means a larger k value leads to a steeper, more negative slope, and a smaller k value leads to a flatter, less negative slope. So the question becomes, how does the change in the half-life affect the value of k? We can use the formula k is equal to ln2 divided by half-life. This tells us that k is inversely proportional to the time it takes for the amount to be reduced to half. So it is inversely proportional to the half-life. If that time is reduced by a factor of 2, as the question states for ciprofloxacin, then k must increase by a factor of 2. Once k doubles, the slope of the semi-log line becomes twice as steep. A steeper slope means a more negative slope, which further means the graph drops downward faster. So this leads directly to the correct answer. Answer choice B. The semi-log plot for ciprofloxacin will have a much steeper slope or a more negative slope. If you found this question to be a little bit challenging, remember this strategy. First, identify what the question stem is really asking you. Second, take any important information, even if it's worded in an unfamiliar language, and connect it back to formulas, equations, or any science concepts you've already known. So, by focusing on these two steps, understanding the question and mapping the results to your background knowledge, you can confidently tackle any difficult questions presented to you. With that in mind, let's move on to the next question. Question number 5. This is a much longer question, and question number 5 reads, in a study, scientists placed Nitrobacter, a genus of bacteria that oxidizes NO2 minus to NO3 minus in the left compartment to serve as the anode. They placed a species of Pseudomonas which reduces NO3 minus to NO2 minus in the right compartment to act as the cathode. Together, they created a functional bioelectrochemical cell that produces a voltage of 3.8 volts. This cell was connected to two separate capacitors. The first capacitor had a capacitance of 4 microfarad, and the second had a capacitance of 8 microfarad. After charging both capacitors to the same voltage, the scientists disconnected the voltage source and measured how quickly each capacitor discharged. They observed that the 4 microfarad capacitor discharged twice as fast as the 8 microfarad capacitor. So, which of the following graphs best represents the result of this study? The correct answer to this question is B. Let's break it down together and see why. First, what is this question asking us? It's asking us to identify the graph that best represents the result of the study. So, what is a key piece of information that will help us pick the correct answer? If you said the result of the study, you are absolutely right. Here's the only sentence you need to focus on. They observed that the 4 microfarad capacitor discharged twice as fast as the 8 microfarad capacitor. That's it. This is the critical sentence. Everything else in the question stem is just background detail meant to distract you. So, what does this sentence mean? It tells us that the rate of discharge is faster for the 4 microfarad capacitor. Remember, we've already discussed that capacitor discharge follows an exponential decay curve. All the graphs shown here represent exponential decay. Now, let's recall what the axes represent. The y-axis shows voltage in volts, and the x-axis shows time in seconds. If the 4 microfarad capacitor discharges faster, that means its voltage drops more quickly over time. In other words, the curve should have a steeper downward slope. It falls off more rapidly. Now let's look at the answer choices. The first thing you should notice is that options A and B look similar to each other, and then options C and D also look similar to each other. But here's a key difference. In A and B, both capacitors start at the same initial voltage, while in C and D, they start at a different voltage. The question tells us that both capacitors were charged to the same initial voltage, so we can immediately eliminate options C and D. Now we're left with options A and B. Both start at the same voltage, but only B shows the 4 microfarad capacitor discharging faster, which appears as a steeper, more negative slope on the graph. That's why answer choice B is correct. This question is a great example of an MCAT-style trap. It gives you a lot of extra information to throw you off. But your job is to stay laser focused on the main idea and the key data point that actually matters. I like to give you questions with varying levels of difficulty so you can build the skill of filtering out distractions, just like what you need to do on the real MCAT exam. So remember, focus on the core results, identify what the question is really asking you, and use your conceptual understanding to guide you toward the right answer. You should now have a solid understanding of exponential and semi-log plots. Next, we're moving into the MCAT passage section of this video. If you feel like you need a quick review, don't hesitate to pause here or rewind to revisit what we have just learned. Mastery comes from repetition, and you've got this. Before we dive into the passage, remind yourself of this. You already have all the tools you need to get every single question right. As you read, focus on the main idea of the passage. If something reminds you of a topic you've seen before, take note. That connection might help you predict the types of questions that follow. Also, pay attention to relationships, comparisons, and overall structure of the passage. All right, with that mindset, let's move on to the passage. I'll read the passage to you first, then pause the video and work through the questions on your own before checking the explanation. Good luck, you're doing great, and let's just begin. Livestock such as goats are prone to E. coli infections, which can cause significant economic and health impacts. In a recent study, researchers aimed to determine the most effective and cost efficient strategy for treating E. coli infections in goats. Pharmacokinetics (PK) and pharmacodynamics (PD) parameters were established to evaluate both the therapeutic efficacy and the potential for antimicrobial resistance. Pharmacokinetics (PK) describes how a drug moves through the body, including absorption, distribution, metabolism, and excretion. Whereas pharmacodynamics (PD) focuses on the biological effects of the drug and its mechanism of action on the body. The, anto- the antimicrobial drug marbofloxacin, figure 1, was administered at a dose of 2 mg per kilogram of body weight on day 1 and again on day 5 of the experiment. Blood samples were collected at multiple time intervals to monitor plasma drug concentrations. Here's figure 1. It says the structure of marbofloxacin. Semi-logarithmic plots of mean plasma concentration versus time for both day 1 and day 5 are shown in figure 2. Figure 2 says semi-log plot of mean plasma concentration time at day 1 and day 5. The slope of day 1 curve was negative 3.38, while the slope for the repeat dose on day 5 was negative 2.41. These semi-log plots follow the general equation ln of AT is equal to minus KT plus ln of A0, where ln AT and ln A0 represent the natural logs of the final and the initial drug concentrations respectively. Here K is the elimination constant and T represents time. Question number 1. Which of the following would result in a steeper downward slope for day 5 plot? Answer choice A says administering a higher dose of the drug. Answer choice B says increasing the clearance rate of the drug. Answer choice C says increasing the drug's duration in the body. And answer choice D says increasing the initial concentration of the drug. Here's question number 2. It says, what is the half-life of the drug in day 1 plot based on figure 2? 3 hours, 1 hour, 0.2 hours, or 0.9 hours? Here's question number 3. It reads, which of the following changes will not affect the slope of the graph shown in figure 2? Answer choice A, decreasing the initial dosage of the drug. Answer choice B, using the drug with a shorter half-life. Answer choice C, faster kidney excretion of the drug. Answer choice D, impaired liver function. Here's question number 4. Which of the following information cannot be extrapolated from figure 2? Answer choice A says the half-life of the drug. Answer choice B says volume of distribution of the drug. Answer choice C says the initial concentration of the drug. And answer choice D says the decay constant of the drug. On this slide, we're going to break down the passage and analyze it step by step. The first paragraph reads, livestock such as goats are prone to E. coli infections, which can cause significant economic and health impacts. In a recent study, researchers aim to determine the most effective and cost-efficient strategy for treating E. coli infections in goats. This opening paragraph is simply an introduction. It tells us the main goal of the study, but it doesn't give us any scientific details or background knowledge that we've seen before. So we note the purpose and move on. The next paragraph says pharmacokinetics (PK) and pharmacodynamics (PD) parameters were established to evaluate both the therapeutic efficacy and the potential for antimicrobial resistance. Pharmacokinetics (PK) describes how a drug moves through the body, including absorption, distribution, metabolism, and excretion, whereas pharmacodynamics focuses on the biological effects of the drug and its mechanism of action on the body. This section introduces PK and PD. This is new information, so all we need to do here is to take note of where it appears in case a question comes up. We can refer back to it later if a question asks. Then the paragraph continues. It says the antimicrobial drug Marbofloxacin, figure 1, was administered at a dose of 2 mg per kilogram of body weight on day 1 and again on day 5 of the experiment. Blood samples were collected at multiple time intervals to monitor plasma drug concentrations. So here they introduce the drug used in the study and give us a brief overview of the experimental procedure. Again, this is new information, so we just note it and move on. Figure 1 shows the structure of the drug, but we don't need to analyze the structure right now unless a question asks us to do. The next paragraph reads, semi-logarithmic plots of mean plasma concentration versus time for both day 1 and day 5 are shown in figure 2. So now they introduce figure 2 and confirm that is a semi-log plot, a concept we've already covered in this lesson. So you don't need to study the figure in detail yet. We can come back to it when a question requires it. Then the passage continues with the slope of the day 1 curve was negative 3.38, while the slope of the repeat dose on day 5 was negative 2.41. These semi-log plots follow the general equation of ln AT is equal to minus KT plus ln of A0, where ln AT and ln A0 represent the natural logarithms of the final and initial drug concentrations. Here K is the elimination constant and T represents time. So here they give us the slopes and the linear semi-log equation. This is some information we've already learned. So we take a mental note that at least 1 or 2 questions will probably involve this formula or the slope. So in summary, the main purpose of the passage is to describe how marbofloxacin behaves and is used as an antimicrobial drug to treat livestock. Now that we have a better understanding of the passage, let's move on to the questions. So here's question number 1. It reads, which of the following would result in a steeper downward slope for day 5 plot? So what is this question really asking us? It's asking us to figure out which answer choice would make the slope of the graph become steeper. Now, what determines the slope of the line? The passage provides us with a linear equation for the semi-log plot, which should look familiar to you. We saw it earlier in this lesson. The slope of this graph is determined by the value of k, which as the passage tells us is the elimination constant. So what happens to the slope when the elimination constant changes? Does increasing or decreasing k make the slope steeper? If you said increasing, you are correct. A higher elimination constant means the drug is being removed faster, which makes the slope of the semi-log plot more negative or steeper. Let's go through each answer choice and see which one is correct. Option A says administering a higher dosage of the drug. Does giving a higher dose increase the elimination constant? What do you think? No, it doesn't. A higher dose just raises the starting point of the curve, the initial concentration, but it doesn't change the slope. So A is not correct. Now, answer choice B says increasing the clearance rate of the drug. This one is correct. The clearance rate and the elimination constant are directly related. Increasing the clearance rate increases K, which means the drug leaves the body faster and the slope becomes steeper. So this option B sounds correct. Option C says increasing the drug's duration in the body. This is the opposite of what we're looking for. A longer duration means the drug stays in the system longer, which means the value of K is smaller and the slope becomes flatter. It doesn't become more steep. And option choice D says increasing the initial concentration of the drug. This just raises the graph upward, but it doesn't affect the slope. The rate at which the drug is eliminated remains the same. So this is also not correct. The correct answer is option B, increasing the clearance rate of the drug. Remember, questions like this are classic MCAT traps. They'll throw you a bunch of fancy words like half-life, clearance, dosage, but only one thing really matters. What affects K, the elimination constant? Once you focus on that, you'll never get lost in the details again. So here's question number 2. It says, what is the half-life of the drug in day 1 plot based on figure 2? This question is asking us to determine the half-life of the drug based on the information provided in figure 2 and in the passage. What equation do we need to solve this? We know that K represents the slope of the graph, and the slope of the semi-log plot for day 1 is given as minus 3.38. Now, how do we relate the decay constant K to half-life? If you said K is equal to ln2 divided by T1 half, you are right. And then once we rearrange this equation, it gives us T1 half, for the half-life, is equal to ln2 divided by K. Next, let's plug in the values. So we have T1 half, for the half-life, is equal to 0.693 divided by 3.38. The negative sign in front of 3.38, that just tells us that it's a downward slope of the curve, so we can ignore it for this calculation. Since we don't use calculators on the MCAT, we will need to round the numbers to make things so much easier for ourselves. So we can round 3.38 to 3 and 0.693 to about 0.7. So T1 half is equal to 0.7 divided by 3, or it's equal to 7 times 10 to the minus 1 divided by 3. That's roughly about 0.2 hours. So on the MCAT, approximating and rounding smartly saves a lot of time and it gets you to the close answer very quickly. So the final answer to this question is option C, 0.2 hours. As you can see, this question was actually quite straightforward. All we had to do was plug in the values into the equation provided in the passage, along with another equation that we already knew from our prior knowledge. The numbers were easy to work with. It allowed us to arrive at the correct answer very quickly. This shows that questions like this are not difficult if we stay focused and apply background knowledge we've already built. With that in mind, let's move on to question number 3 and see how we can answer that question. So question number 3 asked us which of the following changes will not affect the slope of the graph shown in figure 2. So this question is asking us to identify the option that does not affect the slope of the semi-log plot. Remember, the slope of a semi-log decay plot is determined by the value of K, the elimination constant. The passage describes K as the drug's elimination rate constant. So let's go through each option and see which one is correct. Option A says decreasing the initial dosage of the drug, but decreasing the initial dosage of the drug only changes the starting point of the semi-log plot. It does not change the slope. Because the slope depends solely on the elimination rate, therefore this option has no effect on the slope. In option B, using a drug with a shorter half-life does affect the slope. From the decay constant formula, half-life and K are inversely related. A shorter half-life means a larger K, which makes the line on the semi-log plot steeper, so this option does affect the slope. For option C, a faster kidney excretion increases the rate of drug elimination. This increases K, which steepens the slope. It makes the slope more steep. So this also affects the slope. In option D, impaired liver function slows drug clearance, causing the drug to remain in the body longer. This decreases the elimination rate, which changes K, and therefore it changes the slope as well. So the correct answer is A, because decreasing the initial dosage does not affect the slope of the semi-log plot. Here's question number 4. It read, which of the following information cannot be extrapolated from figure 2? Is it the half-life, the volume of distribution, the initial concentration, or the decay constant? So this question is asking us to determine which answer choice cannot be determined from figure 2. Which one did you pick? If you chose answer choice B, you are correct. To solve this question, we only needed to recall what semi-log plots represent. Even if you had forgotten that, you could refer back to the passage and look at the equation provided. From that equation, you can determine the initial concentration of the drug, the decay constant, and using the decay constant, you can easily calculate the drug's half-life. All of these can also be interpreted directly from the semi-log plot. However, the volume of distribution cannot be determined from the plot or from the equation shown. VD requires information about the amount of drug in the body relative to its plasma concentration, which is not provided in figure 2. Therefore, answer choice B is correct. In this lesson, we really broke down exponential decay graphs and semi-log plots. I gave you practice questions with varying levels of difficulty so you can get a feel for how the MCAT might test you. The more challenging questions were intentionally designed to push you, to help you strengthen your reasoning skills and train your mind to analyze passages, identify key concepts, and extract the main idea with confidence. As you can see, these questions become so much easier when you stay focused on what the question is really asking you. When you take the information from the passage or the question stem and bring in your own scientific intuition, you can handle anything the MCAT sends your way. Stay focused, stay confident, and remember, you already have every tool you need to succeed. Mastery comes with repetition, and these videos give you exactly the right amount of practice to get you fully prepared for the test day. With that mindset, we'll wrap up this video here. Keep pushing, keep studying, and trust the process. You've got this, and your MCAT success is absolutely within reach. Thank you for watching.